Okay, welcome back to another Physics 325 remote lecture. This time we're on lecture 28. Where were we last time? We were deriving a method, kind of a fancy, powerful matrix method, for handling very complex systems, like this system of lenses here. And the whole idea was by observing what happens when a beam hits a lens or travels a distance, we can summarize the effect of any optical element in terms of an angle and a displacement, or rather a height above the axis. This allowed us to replace any optical element by a 2x2 matrix, and by crunching a whole bunch of them together, each one of them just corresponds to a matrix multiplication. So at the end of the day, a complex system ended up being 4 numbers. So today we're going to just wrap up some loose ends and start looking at some actual optical systems. So the first thing we're going to do is just do a few examples that will hammer home the point of how you use the matrices. And then we'll look at 2 simple optical elements, the first one being a camera, and the second one being, I guess, the most important optical element, your eyes, and some of the nuances and things we can do to improve images there. Okay, so let's get started. So the first thing we're going to do is prove high school and first year optics. We did this a little bit last class, but I kind of want to hammer home the point. So what we're going to do is first look at the principal rays via matrix optics. So what we're going to start with is a lens on an axis, and the lens will have a focal length f, and we'll place an object somewhere along the axis. It'll be outside of f, and we'll consider f to be positive for this first example. Our first principal ray is the one you normally see where you have a collimated beam coming in parallel to the optical axis. And we'll call that case 1. Case 1, alpha is equal to 0, there's no angle, and we're at some height. Now just recalling what this lens does, it is a matrix, and we're going to assume that it's a thin lens. That was the thin lens matrix that we derived last lecture. So let's just apply that thin lens matrix to our input ray. Just performing the matrix multiplication. We're still at the same height, but now we have a given angle given by h over f. And if we recall, that angle is given by rise over run, so that tan alpha over our distance here, or our distance is equal to negative h over alpha. So in this case, that's equal to, let's find out, which is just the focal length. So we really have to draw this ray going directly through the focal length. Okay, and that's the first principal ray. The next principal ray, you see, is often going right through the center of the lens. And in this case, we have alpha is just some angle, and height is 0. I'm not even going to bother calculating alpha. We'll see why in a second. Notice that we're just assuming that n is equal to 1 here. It doesn't really change anything if it were not. So let's just apply our matrix. And we see that we get the exact same ray out. For our second principal ray going right through the center, the beam is just undeflected. And the third ray that we often use when we're doing geometrical optics is one that goes through the focal length on the object side of the lens, like this. What does that look like? Let's write that down as case 3. In this case, it hits at some height h, so that alpha is equal to h over f. That's the angle we're coming in at, so that the ray looks like this. All right, so we're just going to apply our matrix again. And what do we get? Well, on top we get h over f minus h over f. And on the bottom we get h. So that's equal to 0 h. No angle. It comes out horizontal. So that principal ray looks like this. And those are the principal rays. Now, I see that I've drawn my foci incorrectly. So if I'm going to I'll do some magical editing. And that's how we can derive these principal rays that were used to cast images, or to see how images were formed just geometrically with pen and paper instead of using the thin lens equation. Of course, we can always just use the thin lens equation that we derived last time and get the same answer. So one last thing about thin lenses, talking about virtual images. We talked a bit about negative images last time. Let's just look what it, see what it looks like. So we'll do the same sort of thing, except now we'll put the object a bit closer. Let's see what the thin lens predicts. Let's just make it simple first, the thin lens equation. It tells us that we should expect the image to be located at a negative distance. That means behind a distance f. So geometrically, this is just an important point here. Let's see what that actually looks like. We're still always able to use our principal rays here. So there's our first principal ray, and let's draw our second principal ray. And we can see that the rays are diverging. Now the way this is normally handled is you just move backwards along both, and that's a terrible line, I'm sorry. You get the idea. You draw the image here, and it looks a bit different. First of all, it's not flipped upside down like the last one. It's also bigger. But why is that valid? Well, if you think about it, this is just each point there, the point that we just drawn, is a spherical wave. But if you ask an observer who's skeptically sitting there on their chair, looking at that ray, from their point of view, this is identical to a point that is emitted behind the lens, a distance f behind the lens, as we predicted. And so in principle, if our imaging system was perfect, we could remove the lens, replace the object with one which looks like twice as big here and twice as far away from where the lens was, and the observer would not be able to tell the difference from their vantage point. So a virtual image really appears like a real image as long as you have an imaging system to pull it in. Okay, that's the first important point. Another thing that we come across is magnification of a system. So if we just draw our standard situation as we had before, we have an object of height HO and an object of height image of height HI, and their distances DO and DI respectively away. So let's just look at these two triangles that they form. These are similar triangles, so that HO over DO is equal to HI over DI. And the magnification, if we think about what a reasonable definition of it is, it's how much bigger or smaller the image appears than the object. So technically this is what we call the transverse magnification. And from geometry we can see that it's negative if it's flipped upright this way. So we're going to insert a negative sign, and this is equal to, from the similarity of triangles, D image over D object. That's the magnification, the transverse magnification of our imaging system. Okay, final loose end from our simple optical elements. There's one more important optics element that has a matrix that is used quite a lot in astronomy, and that's a reflecting curved mirror. So a curved mirror will act like a lens, it turns out. And we see these in larger optics more than smaller optics, because for smaller optics it's easy to make a small transparent lens that can support its own weight. But for large systems, it turns out it's much easier to put a thin reflective coating on an element which can be opaque but has a lot of mechanical strength. And so therefore for telescopes, you often see either single monolithic reflective surfaces or mirrors that are made up of many individual reflective surfaces that do not have to be transparent all the way through. So it's used a lot more in astronomy. And let's figure out how exactly a mirror should work. So let's look at that case here. And we're looking at curved mirrors. So let's draw that. Here's a generic situation. We have a curved mirror, radius of curvature r, and we have a beam coming in at some angle, and it reflects at that height h as such. So it's going to come in at some angle, reflect, and then bounce off. So I happen to have chosen a very shallow angle, but let's just roll with it. This is the angle that we normally talk about when we're talking about our thin lenses, right? Our alpha. We'll call that alpha in. And similarly, alpha out is reflected there. And from geometry, this whole angle here is also alpha out. Okay, so that's the setup. How do we calculate this? Well, the one thing we know is the law of reflection. What does the law of reflection say? Remember those good old days when the course was simpler? We're deriving the law of reflection. It says that the angle of incidence is equal to the angle that is reflected. Let's draw those. The law of reflection says that theta I equals theta r, where we're measuring with respect to the normal of the surface. Okay? Good. Okay, so that's the setup. We know that theta I is equal to theta r. What else can we say? Well, we see that by inspection, if theta I is equal to theta r, we can write that alpha out, it's equal to alpha in plus theta I plus theta r, right? That's this angle here. So alpha out, and since theta I is equal to theta r, we can write that like this. And the beam is now going to the left. We're going to call that positive. And that means it's as if the angle is now tilted down, where it was originally tilted up. So we're going to put a negative sign here. Okay, just a sign convention. It's always hard to, when you have reflections among symmetry. So if the angle is positive, it's increasing when it's going to the right. And it's going to the left now. We'll call the reflected angle also positive. So we have to put a negative sign to say it's going down now instead of going up. Okay, bit confusing, but that's what we've got to deal with. What else can we say? Well, can we write alpha in as anything? Turns out we can. Let's call this angle with respect to r, we'll call this phi. And it's going to be hitting at some height, h. Okay, it's getting a bit complicated, but let's just write this down. We're going to write sine phi is equal to h over r. That's approximately equal to phi, because we're in the small angle approximation. What else can we say? Well, we can use geometry again. And that phi is also equal to this phi here. All right? Whew. So that's equal to alpha in plus what? Theta. Theta in. Okay. So now we can actually just combine these two things. So we have h over r is equal to alpha in plus theta in. And that will allow us to derive what this thing should be doing. So we can eliminate theta in effectively. Okay, so we can plug that back into this equation right here and find that alpha out is equal to alpha in minus 2h over r. So let's write that in matrix form and do that same kind of game that we did before. So let's write this as that the angle is now alpha in minus 2h over r, and the height has not changed because it's just a reflection. It hasn't propagated at all. That's equal to some matrix times our input. And the only question is, what are the matrix elements? Let's figure those out. So for the first element, whatever we need to multiply a times alpha in plus b times h should give us alpha n minus 2h over r. So by inspection, we can write that as 1 and negative 2 over r. And then in the second one, alpha times c plus h times d should be h. C is equal to 0, d is equal to 1. And that is the matrix for a reflecting mirror. But look at this. This is exactly the same form as the matrix for a lens. So if we let the focal length, the effective focal length of this mirror, to be half of its radius of curvature, then we just have something exactly like a lens. Exactly like a lens like that. So either way, we have the matrix for a lens or a mirror is 1, negative 1 over f, 0, 1. And for a mirror, the focal length is r over 2. And for a lens, if we remember, it was just given by this. Just as a quick note, the dioptic strengths add. So if we have two lenses, or biconvex lens, as it's called, that's R2 and R1. Okay, so those are matrices for lenses, propagation, and reflecting mirrors.